the study and we'll look at this and kind of approach it as though it were the test. So if you downloaded this document, you can look on your own sheet. But if not, you can look on my sheet, and we're going to approach this as though this were the test, and then I'm going to show you how it would be graded if it were the test. The main difference between the tests in here and the tests that you might have in another class is the multiple choice questions. Notice the instructions for the multiple choice questions. Select all correct answers. There may be more than one correct answer or no correct answers. No answers may be correct. To select a correct answer, underline both the letter and the text following the letter. So I'm sure you've all had a test where the last option, you can go to A, B, C, D, E or whatever, and the last option says all of the above or none of the above, or some tests it might say both B and D are correct, something like that. On our tests, we don't have anything like that. For every question, all the answers might be right, none of them might be right, some of them might be right. So what you're going to do on the test on Monday to select a correct answer on the multiple choice, you're going to, if you think, for instance, A is a correct answer, you're going to choose everything starting with the letter A, going through the length of the answer, and you're going to underline that. When you get done answering all the questions, the best way to do this is to download the document onto your computer or your tablet, whatever you're using. Answer the questions, save it, and then send it in through D2L. So I'm going to underline this. And what I'm going to have you do now is look at, on these sample questions, there are 4 questions, 4 multiple choice questions. So I'm going to give you a few minutes and I'm going to have you select all the answers that you think are correct. If you downloaded this document, you can go ahead and mark your answers on the document you downloaded. If not, I've got all the questions in view, so you can just decide which answers you think are correct. All the answers that you think are correct, if you were working this on the test, you would underline. If you don't think they're correct, don't underline them. So I'll give you about 5 minutes to work on this. I've got 5 after according to the clock on the computer I'm using. So I'll give you till about 11 or 12 after. If you want to, look up some answers, you can look up some answers, but try to finish in about the next 7 minutes, and then we'll talk about what the correct responses would be.
Sorry, I just got in here. Are we supposed to be taking this?
Yeah, this is just the study guide for chapter 1. So just look at these questions. If you downloaded the document, you can open the document and do it, on your own computer or laptop or whatever you're using,
Okay.
tablet.
Okay.
If you didn't download it, then you can look at mine and just select any answers that you think are correct for these first 4 questions. And in a couple of minutes, we'll talk about what the correct responses would be. Is anyone still working, or can we look at the answers now? Let me know if you're still working. Okay, I don't hear anybody saying that they're still working, so we'll look at the correct answers. According to cell theory, well, one correct answer would be cells come from other cells. A second correct answer would be that all living organisms are made of cells. Remember, those are the 2 parts of cell theory. When does a scientist form a hypothesis? After the data has been collected and analyzed, before they decide what problem they're studying, only if the hypothesis is ready to be accepted as a theory, or only when he has to communicate the study to other scientists. Well, remember the order of the steps of hypothesis testing. First, you ask a question or define a problem. Next, you do some background research. And then the third step is you make a hypothesis. Then you test the hypothesis in an experiment. So really you do the hypothesis after you do the background research or before you do the experiment. So notice for number 2, there is no correct answer listed, so you wouldn't choose any answers. What characteristic of living things determines the other characteristics? Well, remember we said the factor that really controls all the characteristics that we see in living organisms is the DNA. Now, notice if you think about a question like number 3, when I write the questions, I try not to give you a hint whether there's more than one answer or just one answer or no answers. But if you think about what number 3 is asking, what characteristic determines everything else? You know, there can really only be one thing that determines all the other characteristics. So sometimes there is a hint in the questions, even though I try not to give you one. Kind of like if I would ask you, who is the tallest person in class? There's probably only one answer to that question, unless, you know, 2 people are tied for the same height. What did Darwin's ideas about evolution include? Well, variation. Remember, we said he was the first biologist who recognized that. The inheritance of characteristics. We said this was one of his ideas that was kind of problematic. And natural selection. So for this one, all of the answers would be correct. So let's look at these 4 multiple choice questions. Now, the way the test is graded is each answer, whether it's right or wrong, is worth 1 point. So question number 1 would be worth 4 points if this question were on the test. If you chose B and C and didn't choose A and D, you would get all 4 points. If you chose B and you didn't choose A and D, but also you didn't choose C, then you would miss 1 point for not choosing C. So if you choose an answer that you shouldn't choose, or if you don't choose an answer that you should, that's minus 1 point. So these 4 questions together, notice number 1 is worth 4 points, 2 is worth 4 again, 3 is worth 5, number 4 is worth 6. These 4 questions would be 16 points, and your score on these 16 would be minus however many you missed, you selected incorrectly. I didn't include any sample true and false, but there are some true and false questions. Notice that there have been some studies done of how students learn and take exams. And one of the things that these studies have shown is that if students don't know and they have to guess for their answer on a true false question, they tend to guess true because they want to, you know, they think their teacher is going to tell them something that's correct. I guess it's kind of natural. But keep in mind, that means you have to be careful because there's kind of a built-in bias that you're going to be more likely to choose a question as true than false if you don't know the answer. Our tests pretty much always have a short answer question, and you'll see some instructions similar to this. Please use correct grammar and complete sentences. Be specific and make sure that the answer is in your own words. There's usually 2 points on grammar and complete sentences. So if you have a run-on sentence like a comma splice, or if you have an incomplete sentence, there's no subject or verb or something, usually you lose a point each time that happens. So what's the difference between a hypothesis and a theory in science? Now on the test, you'll see how many points that this question is. Afterwards, it might say, you know, 5 points or 6 points. Now, if you think about what I just told you, the fact that there's usually 2 points for grammar and writing your answer in a complete sentence, you know, if the test told you that this was worth 5 points, well, 2 of those points are for grammar, so that means there's 3 more points left. So in your mind, you should be thinking, okay, there's probably 3 different things that I'm going to have to tell him. So in this case, if we look at this, we could say something, and keep in mind there are different ways that you could answer this. So I'm just going to give you one example. A hypothesis is a possible explanation. Remember, we said a hypothesis isn't necessarily correct. Something observed in nature, or the results of a previous experiment. Remember, we said that's basically where the two ideas for a new experiment come from. If we look at a theory, theory is a hypothesis, but it's a hypothesis and it's been tested in many experiments. Now, many could be a dozen or 100 or 1,000, it depends, but it's been tested in many experiments. And it's never been rejected. So what does that mean? Scientists are pretty certain that it's correct. Remember what we said, technically we're never sure that something is correct. The next experiment could prove it wrong. So your answer would be something like this. So if you left out some of these parts, you know, there are kind of some main ideas here. So a hypothesis is a possible explanation, either for something observed in nature or for the results of a previous experiment. And a theory is a hypothesis that's been tested in many experiments. It's never been rejected. So scientists are pretty sure it's correct. So depending on how many points this was, you know, if this was 8 points, there would be 2 points for grammar. And then a hypothesis is a possible explanation would be 1 point. For something observed in nature would be another point. For the results of a previous experiment would be another point. So if you left some of these parts out, you might lose a point. Or if you put in something that was completely wrong. We've said that all living organisms are made of cells. So somewhere in here, if you said all living organisms are made up of a hypothesis, you would lose a point for something like that. So it's usually not good to just add some things in if you don't think that they're actually part of the answer to the question, because you can lose points for stuff that's incorrect that you put in. Now, besides this, remember what we said that first day. You should also be able to answer some questions. You might have some matching, or you might have some questions that are sequencing where you have to put things in order. Or you might have some questions that are fill in the blank. So there's typically a variety of different types of questions on the test. And as I mentioned, there's no true false here, but there's usually a couple true false. Now, keep in mind, when you think about the multiple choice, you know, if you look at number 3, there are 5 answers. So this question is worth 5 points. The short answer question on the test will tell you how many points it is. But in general, for all the other parts of the test, each question is just worth 1 point. So this means true false questions are only worth 1 point. So don't obsess over 1 point on a true false question and spend so much time on the true false question that you never get to some of the other questions. One of the ways to take a test, not just in this class, but in any class, if you don't have to do the problems in order, the first thing you should do is go through the test and do all the questions that you think you know the answer to. Because if you run out of time at the end of the test, you don't want to miss answering the questions that you knew. You want to miss answering the questions that you didn't know the answer to anyway, and you're just going to guess on. So always start out, do the questions that you think you know the answer to. It's also good to answer a few questions that you think you know right at the beginning, because if you answer a few questions that you think you know, it puts you in a positive frame of mind. And you know, whether you're in a positive frame of mind or a negative frame of mind, that can have a big impact on any type of performance. If you start with number one and you don't know the answer to number one, and then you do number two and you don't know the answer to number two, and then you look at three and you don't know the answer to that, you're ready to hand in your test because you know you're not going to do very good. So I would recommend skip around, do a few questions that you know the answer to first so that you kind of get rolling. And then if you want to go back to number one and start with number one and work your way through, that's fine. It's also good to, at the end, before you turn it in, go back and double check and make sure you answered all the questions. I'm not sure what the best way to approach the multiple choice questions with more than one answer is. In the past, I've had some students who have told me that the best way to answer these questions is if you don't know, don't mark any answers. I've also had students who have told me if you don't know, the best strategy is to mark all the answers. Of course, as a teacher, I'm going to tell you that the best strategy is to know the answers. So we'll have our test on chapter 1 on Monday. This is a relatively short test. There's only about 20, 25 questions. So whenever we do have a test, the test is always at the very beginning of class. I know if it's not till the end, you're not going to be paying attention. So it'll be at the beginning. So even though class starts at 9, the test will probably be posted at about 10 till 9. And then there will be some instructions on the test, but you'll have till 9:55 to turn in the test. So keep in mind, this is a relatively short test. So, you know, if you were so inclined, you would probably have some time to look up some of the answers. But some of our later tests are going to have more questions on them. The topics are going to be more complicated, and you won't have time to look up all the answers. So one of the things I would suggest to get in the habit of how to study for our tests, over the weekend, go back and look at the notes. Hopefully you've downloaded our notes, but if not, they're still up there. So download our lecture notes. They're in Word format and they're also in PDF format. So if you have a preference, you could use either one. So look over the notes. Yesterday after class, I sent you a link to the YouTube site so you can go back and review the videos. Has anybody tried going to the YouTube site to double check if that link worked? I tried it, but it's always hard to tell since I gave you the link. If not, and you try over the weekend and you don't have any luck, let me know. But I would recommend, you know, read the book if you haven't read the book yet. Look at our notes, review the videos if you want. And really the answers to most of the questions will be somewhere in that material. Now, I'm not going to tell you that the answers to all the questions will be in that material for one simple reason. Part of what we're trying to do here is learn to think like a biologist. And that means that we can't really do that if every question I give you, all you have to do is know what we said some other time in class or have read the book. So there are some questions that require you to think through them. Now, we may not have talked about exactly what that question is, but if you think about something that we've done in class that was similar, that should provide some guidance for how to approach that question. So there are some of the things that you have to use kind of a logical analysis and read the question carefully and figure things out from there. Are there any questions about what the test will be like Monday? So the test will probably be up a few minutes early. I think I said about 10 to 9. You can work on it till 9:55. What you're going to do is similar to the homework assignments. You're going to download the test, type in your name, You know, underline your answers. If there's a short answer question, you're going to answer it. If there's true, false, you're going to write true or false or T or F by each question, however you want to do it. So there will be a set of instructions with each set of questions. So it's always a good idea to make sure you read those instructions. And then after you hand in your test, and as I say, that will be due at 9:55. Keep in mind that since this is on the computer, when you hand in your test, it is time-stamped. So if you turn it in and it's time-stamped after 9:55, that will be counted as a late assignment, which means on a test, that's a 10% deduction. So make sure that you turn it in on time. So keep an eye on the clock. After that, we'll have a break. And then at about 10 after 10, we'll resume class. And we'll still have some lecture material after that. Any questions about what we're going to do on Monday? Okay, if not, then I'm going to stop sharing this screen and we're going to go to another screen and focus on our next major topic. Now, notice that this next major topic is chemistry. And even though we're going to start talking about it today, this is not on the test on Monday. This will be on the next test, the test over chapters 2 and 3. And this will probably be in about another week or week and a half. Chemistry takes us a little bit longer to get through than chapter 1 did. In your book, chemistry is covered in 2 chapters, chapters 2 and 3. So when we look at chemistry, chemistry is the study of the composition, structure, properties, and reactions of matter. If we look at the universe around us, the entire universe is made of 2 types of stuff. One of these things is matter, and the other thing that makes up the universe is energy. Now, matter has 2 properties. Matter has mass. And mass, in a sense, is really a measure of the amount of stuff in the thing that we're looking at. So we could look at your mass, and that would be the amount of stuff in you. Now, from a chemical standpoint, when we say the amount of stuff, we're talking about the amount of atoms, the size of those atoms. So matter has mass, and you could think of mass as being like weight. It's a little bit different, but it's close enough. It gives us an idea what we're referring to. Matter also has volume, and volume just means that it takes up space. Now, some type of matter have a very definite shape. For instance, my computer is sitting on a wooden desk. This desk has a definite volume. On the other hand, there's some types of matter that don't have a definite shape. If we have some water, you can pour your water into a tall, skinny glass or a short, fat mug. It's still the same amount of water either way. It still has the same amount of matter. And some matter, like gases, like air, they can kind of bend and flex so much that you can walk across a room. You can walk through the air. You can push it aside without any effort. Now, when we look at all this matter, whether it's something that's solid, whether it's a liquid like water, whether it's the gases in the air, matter is made up of some basic building blocks that we call elements. And there are actually 118 different elements that we've discovered so far. Quite possibly there are more that we just haven't discovered yet. Now, despite the fact that I'm saying there's 118 elements, only 98 of these elements occur in nature. So there are 98 of these elements that, you know, if you would be prospecting in the earth, or if you would be taking a rocket ship and landing on an asteroid or going to another planet, there are 98 of these elements that you might encounter. Well, what about the other 20? What about the 20 that don't happen in nature? These elements have only been observed when we do nuclear reactions in physics labs. So we haven't seen them in nature. It doesn't necessarily mean that they aren't out there, but we haven't observed them yet. Now, when we look at the elements are organized into something called a periodic table. And I'm going to magnify this for just a moment so that it's a little bit more legible to show something that I want to show. If we look at our periodic table is a bunch of squares, and it starts with number 1, which is H, hydrogen, and it goes all the way down to number 118, which is lawrencium. And basically, this is how the elements are organized. So after number 1, hydrogen, we go to number 2, helium. And then the next element is number 3, lithium. And then number 4, beryllium. And then number 5, boron. So when we look at this periodic table, this organizes all the elements. And we want to keep this in mind because what we're going to talk about in a moment is what this organization reflects. So notice that the numbers are basically in numerical order, starting with number 1, then we start number 3 here with lithium, and then we start number 11 here with sodium, and number 19 here with potassium, all the way down to 118 lawrencium. So let's think about these elements. If you would pick up a piece of one of these elements, for instance, a piece of pure carbon, you might be able to see pure carbon, or a piece of pure gold. If you would pick up this, what you see is that when we look at these elements, we don't like to write out the whole names. So we use something called their chemical symbols. And the chemical symbols come from their names in Latin. Now, a lot of the English language comes from Latin. So usually the chemical symbols start with the same letter as the name in English, but not always. Now, the chemical symbol is either 1 letter or 2 letters. The first letter is always capitalized. So if there's only 1 letter, it's capitalized. If there's 2 letters in the chemical symbol, the first letter is capitalized, the second one is lowercase. So here are some of the elements that we'll probably talk about and use as examples of various things during the semester. So carbon, capital C, hydrogen, capital H, oxygen, capital O, nitrogen, capital N, phosphorus, capital P. Now notice, here's a weird one, potassium, capital K. This is because the Latin name for potassium starts with a K. So in most cases it's the same, but notice sodium is capital N, lowercase a. Chlorine is capital C, lowercase l. Iron is capital F, lowercase e. So these are some of the elements, and notice this is about a dozen of those 118. About 40 of those 118 elements are found in living things. So this isn't all the elements that are found in living things, but this is some of the most important elements that are found in living things. So let's look at an atom. A few hundred years ago, when people had just started talking about atoms, we thought that atoms were solid pieces, very small, but solid pieces. And what we've learned in the last 200 years is that atoms are actually made of smaller pieces themselves. And these smaller pieces are called subatomic particles. Now, sub means below. A submarine goes below the water. So subatomic particles are below the level of an atom. They're smaller than an atom. And there are 3 types of subatomic particles. There are protons, neutrons, and electrons. So let's look at these 3 types of particles. And here we have a representation of a carbon atom. And we have some blue circles. Now there's really 6 blue circles in here, but 2 of them are hidden behind some of the other blue circles are some of the kind of pinkish red circles. These blue circles with the plus sign in them represent what we call protons. There are also 6 neutrons in here, these pinkish reddish circles. And again, I can only see 5 when I look, so I think that means one of them is hidden behind the other ones. Imagine that you're looking at something 3-dimensional here. And then finally, we have electrons. And the electrons are these green things, and notice they have a negative sign in them. In just a moment, we'll see why we have a positive sign inside the protons and a negative sign inside the electrons. So when we look at atoms, atoms are often represented like a diagram of the solar system. If you think about diagrams of the solar system that you saw when you were in grade school, probably still now even actually, in the center of the solar system is the sun. In the center of our atom is an area called the nucleus. And the protons and neutrons are found in the nucleus. Out around a model of the solar system orbiting the sun, we would have all the planets. Here, orbiting the nucleus, we have the electrons. And notice there are 6 electrons. We can see the 6 electrons here. Now, this is kind of a good way to visualize things. It's a nice, simple way to think of things. It's not completely accurate. For instance, when we look at electrons, electrons are kind of defy what we think of with common sense. We can have an electron here, and the electron can jump all the way over here, and it can jump all the way over there without going through the space in between. Electrons can basically, kind of like, beam me up Scotty on Star Trek. Electrons can go from one location to a next, and they never pass through the space in between. So in this case, with the planets, if we were looking at a model of the solar system, we can see where a planet is today, and we can predict where it's going to be tomorrow because the planets follow nice, regular, predictable orbits. With an electron, just because we know where it is right now, we can't predict where it will be in 10 minutes or 10 seconds or tomorrow because they can pop through space. This is what we study in a field of science called quantum mechanics or quantum physics. And it's very challenging. It's very advanced math. So let's think about protons first. So the number of protons in the atom is what we call the atomic number of the atom. And this identifies what type of element it is. So the atomic number is actually the number that's written inside the little squares on our periodic chart. Hydrogen has the number 1 written here. So that number 1, hydrogen is atomic number 1, and it has 1 proton. Helium is atomic number 2. So helium atoms have 2 protons. Carbon is atomic number 6. They have 6 protons. Uranium is atomic number 92, and uranium atoms have 92 protons. So when we think about the number of protons is the atomic number, and this tells us what element we're looking at. If we're looking at an atom of carbon with 6 protons and something happens, so it loses a proton, so now it only has 5, it's not carbon anymore. Or if something happens so it gains a proton and now it has 7, it's not carbon anymore. Carbon atoms have 6 protons. That is what makes them carbon. As we'll see later, the number of neutrons, the number of electrons isn't always the same, but if it's carbon, it has 6 protons. And in fact, the number of protons can't change in a normal chemical reaction. Remember, we said that the center of our atom is a spot called the nucleus. You've all heard of nuclear reactions. Nuclear reactions change the nucleus. So the only way the number of protons in our atom can change is in a nuclear reaction, not in a regular chemical reaction. A nuclear reaction is different than a chemical reaction because it changes the neutrons or the protons. It changes the two things that are found in the nucleus. Now, if we look at our protons, protons have 3 important properties as far as we're concerned. Protons have a mass of 1 atomic mass unit. Remember, we said one of the properties of matter is that matter has mass. So carbon has a mass of 1 atomic mass unit, which is often abbreviated as AMU. And when I say atomic mass unit, this is a very small measure, but think of something like a gram in the metric system or something like an ounce in the English system. So carbon has 6 protons, so it gets 6 mass units from its proton. Every proton has a mass of 1 atomic mass unit. Every proton also has 1 positive electrical charge. So since a carbon atom has 6 positive protons, it has a charge of +6 from those protons. They each contribute a charge of +1. And the third crucial factor is one that I've already mentioned, which is these protons are located in the center of the atom, in the nucleus. We don't find the protons out here with the electrons. They're always in the middle. Now let's think about our neutrons, these kind of reddish, pinkish balls. And in some ways, neutrons are very similar to protons. Neutrons are also found in the middle of the atom, in the nucleus. The protons and neutrons are kind of smushed together in the nucleus. Neutrons also have a mass of 1 atomic mass unit. So their mass is almost exactly the same as that of a proton. Neutrons typically have a mass that's just a little bit higher, like 1.0005. So not much, but a little bit. So we just round it off and say 1 atomic mass unit. And in fact, if we're trying to find the mass of an atom, all we do is we add the protons plus the neutrons. So for carbon, there are 6 protons, there are 6 neutrons. So the atomic mass for this atom of carbon is 12. Now notice, since we have to add the protons plus the neutrons to figure out the mass, as long as we know 2 of these things, we can always figure out the third. If we know the protons plus the neutrons, we add them, we get the mass. If we know the mass and the protons, say I tell you that there's a type of carbon that has a mass of 14, and there really is. Since it's carbon, it still has 6 protons. So if we take an atom of carbon 14, so if we take 14 minus 6 for the protons, there are 8 neutrons in that atom of carbon. So when we look at neutrons, they're in the nucleus, like the protons. They have a mass that's about the same as the protons, but there's one crucial difference. If we look at the neutrons, notice the neutrons don't have a plus sign in them or a negative sign in them. Neutrons are electrically neutral. They have a charge of 0. So it doesn't matter how many neutrons are in an atom. It doesn't change the number of positive charges. It doesn't change the number of negative charges. So now I talked about carbon with a mass of 14 instead of this carbon would have a mass of 12 because it tells us there are 6 protons and 6 neutrons. Well, remember a minute ago, I said the number of protons is always the same in carbon. There's always 6. The number of neutrons is not always the same in carbon. Some carbon atoms have 6 neutrons, like this example, but there are some carbon atoms that have 7 neutrons. And there are some carbon atoms that have 8 neutrons. And this is true for most of the elements. There are different varieties of their atoms that have different numbers of protons. So for instance, here's hydrogen. Hydrogen is atomic number 1. So when we say that hydrogen is atomic number 1, there's always 1 proton. So the proton is the little blue ball inside. It's got a P with a plus sign. But there's one type of hydrogen that we usually call hydrogen 1, or sometimes just H-1. The 1 is this hydrogen's mass. So remember, mass is protons plus neutrons. So if we have 1 proton and the mass is 1, that means there's no neutrons in this hydrogen. There's some hydrogen that we can designate as H2. It's sometimes called deuterium. Deuter means 2. And hydrogen 2 has 1 proton and 1 neutron. So the mass is 1 plus 1, the mass is 2. And there's some hydrogen that has 1 proton and 2 neutrons. So it's sometimes called tritium. Think of a tricycle. Tri refers to 3. So tritium, hydrogen 3 or H3, has a mass of 3. 1 proton plus 2 neutrons equals 3. Now, these different isotopes, these different versions of the atom, are called isotopes. Iso means the same. Remember, somewhere back in math, you talked about isosceles triangles that had 2 angles or 2 sides that were the same. So when we look at isotopes, pretty much all the elements have more than 1 isotope. There's a carbon-12, a carbon-13, and a carbon-14. When we look at isotopes, some isotopes are stable. And when we say that they're stable, we mean that nothing happens to this atom. It stays hydrogen. If we could take 1 atom of hydrogen 1 or 1 atom of hydrogen 2, and we could put that in a test tube so we could keep track of it, we could come back in a week or a month or a year or a century, and that 1 atom would still be there. Nothing would have happened to it. But some isotopes, like H3, some isotopes are unstable. And after a while, they change into a different element. Well, think about what I just said. We have an atom and it changes into an atom of a different element. Remember that the atoms of different elements have different numbers of protons. So to change the number of protons, we have to have what's called a nuclear reaction. So if we look at H3, if we look at tritium, tritium is unstable. Tritium gradually changes into helium, the next smallest element. Hydrogen is the smallest. If we look at hydrogen or anything like it that changes into another element, these elements aren't usually called unstable. They're called radioactive. So when we talk about things that are radioactive, we're really talking about atoms that go through a nuclear reaction. So hydrogen with 1 proton can change into helium that has 2 protons. We're not going to go into most of the details on the chemistry. That's what chemistry classes are for. But if you're really dying of curiosity, let me know and we can meet and talk about it. So what does this mean? Well, this means if you have an atom of hydrogen 3 and you come back in a week or a month or a year or a century, you might not have any hydrogen 3 anymore. That atom of hydrogen 3 might be an atom of helium now. So radioactive elements go through nuclear reactions. So when we think about those two things, nuclear reactions and radioactive, those are associated with each other. And notice, tritium, hydrogen-3, is found in nature. So sometimes we have the mistaken idea that all radioactivity is the result of nuclear bombs or nuclear power plants or something like that. But that's not actually true. There are radioactive atoms in nature. And in fact, we all have radioactive atoms inside our bodies. Most of the atoms in our body are not radioactive, but we all have some. Depending on what your diet is, some people or animals, it doesn't have to be just people, some living organisms have more radioactive atoms than others. So when we look at these isotopes, some isotopes, an atom can change into a different type of atom very quickly. Some isotopes, a radioactive atom changes into a different element very slowly. It can take a couple of hours to happen. It can take a few days. It can take millions of years to happen. So things that are radioactive kind of have different time frames associated with them. Now we can measure these time frames, and when we measure them, we can talk about what we consider to be something called the half-life of a radioactive atom. And a half-life is the time that it takes for half of our original atoms to change into atoms of the second element. So half of our H3, half of our tritium atoms, to change into helium atoms. So for H3, for tritium, the half-life of tritium is 4,500 days. So we use tritium in a lot of medical procedures. If we want to find out, for instance, where water is leaking out of a blood vessel in your body, one way that we can do this is, water is H2O, you probably know. So the H tells us that there's some hydrogen in there. We can make water that has radioactive tritium in it. And then we can inject this water in you and we can follow where that radioactivity goes. So let's suppose that we inject a patient with 128 atoms of tritium and there's no helium in this sample. After one half-life, after 4,500 days, half of our tritium atoms change into helium atoms. Now notice, it's not necessarily exactly half, and the reason it's not necessarily exactly half, think of this like tossing a coin. If you could imagine that every tritium atom tosses a coin, and heads, it stays tritium, tails, it changes into helium. Well, you know, you could flip a coin 128 times, you might not get exactly 64 heads and 64 tails. You'd probably get close, but yeah, you might not get exact. So this is on average what we see, but it's not what we see in every instance. So now one half-life has gone by. So now when we start the second half-life, we only have 64 atoms of tritium. So now for the second half-life, half of our tritium changes into helium again. So we started with 64 atoms. So 32 of those atoms change to helium. So now our total helium is 64 plus the new 32 that changed. So now we've got 96. Notice that our number of helium atoms and our number of tritium atoms always add up to 128. Now for the next half-life, we start out with 32 tritium atoms, and during this half-life, 16 of those change. So now we're down to only 16 atoms of tritium. We're up to 112 atoms of helium. And notice every time we go through another half-life, we cut our number of radioactive hydrogen atoms in half, and we add that same number of atoms to our helium sample. Now, notice eventually we get down to 1 atom. So what happens now? Well, remember I said this is like a coin toss. So we toss the coin. If we get heads, this 1 atom stays around as a tritium atom. If it gets tails, it changes into helium. And keep in mind, these atoms aren't really tossing coins. I'm just saying that it's a 50-50 random process. So by looking at the ratio of tritium to helium, we can tell how many half-lives have gone by. Notice if our sample is 50% whatever the original atoms were and 50% new atoms, 1 half-life has gone by. If our sample is 25% of the original atoms and 75% of the new atoms, 2 half-lives have gone by. So by looking at the ratio, we can calculate how many half-lives have gone by. So we can estimate when this sample formed. Now, when we use radioactive hydrogen in a medical procedure, we're usually just interested in seeing where it ends up. But radioactive atoms have other uses. Most of the carbon that's around is carbon 12, which is stable. But there is some carbon 14 found in the environment. And since carbon is found in carbohydrates and proteins and lipids and DNA, that means you have some radioactive carbon 14 in your body. And radioactive carbon 14 has a half-life of 5,730 years. Now keep in mind, we didn't figure this out by watching radioactive carbon for that long, but we can watch it for a few years, and then there are some math equations that we can use to extrapolate and figure out what the half-life is. And carbon gradually decays into a form of nitrogen, one of the other elements. Now, since carbon is found in living things, proteins, carbohydrates, lipids, DNA, that means that carbon is found in your body and my body and everything's body. So people who study ancient cultures sometimes use something called carbon dating. Because if we look at ancient cultures, a lot of times they used wood. They might have built their house from wood or built a corral to keep animals in. They might have used animal skins, or they might have used cotton or some type of plant material to make their clothing. So when we find this, or every once in a while, we might even find the bones of some of the inhabitants, and if they're well enough preserved, we might be able to look at carbon in their bones. But we can find the ratio of the carbon 14 to the nitrogen that it changes into. And we can estimate, okay, how long ago were the trees chopped down that were used to build this house? Or how long ago was the cow killed that provided the leather used to make this clothing? So we can estimate how long ago some culture that we're studying actually was around. Now, some radioactive isotopes have half-lives in the millions of years. And again, humans haven't been around that long, so we haven't been watching these radioactive isotopes for millions of years. But if we look at these radioactive isotopes that have half-lives of millions of years, we can also use them to calculate dates. However, we don't have any human cultures that old, but what we do have is we have fossils of organisms. For instance, dinosaurs went extinct about 66 million years ago. So we can calculate how old some of these organisms are, usually not from materials that are in their body, but for instance, if a dinosaur was killed by a volcanic eruption, a lot of volcanic rocks have different radioactive elements in them. And so we can tell when this volcanic eruption happened. Now, sometimes it gets tricky. It's hard to tell if the dinosaur was killed by that eruption or, if the dinosaur died later and then fell into the lava that came out of the volcano. Now let's look at our third type of particle. We spent a lot of time looking at neutrons, but remember we said we have three types of particles: protons and neutrons and electrons. And electrons are kind of the odd man out. They're very different from protons and neutrons. Electrons are so light, they have so little mass that we can ignore it. In fact, the only time we really have to worry about the mass of electrons is if we're talking about nuclear reactions, because nuclear reactions can make a lot of energy from a little bit of mass. But under normal circumstances, if we want to find out what the mass of an atom is, to find the atomic mass, we just add protons plus neutrons. One way to think about electrons is, look at your hands or feel your ears. If you're wearing a ring or if you've got some earrings in your ears, imagine getting up in the morning and you get on the scale in your bathroom and you say, oh, I'm not very happy with that. I didn't know I weighed that much. I know what I'll do. I'll take off my earrings and the rings on my two fingers and I'll step back on the scale. Yeah, you're in for some major depression because when you take off your earrings and your ring, unless they're really humongous, you're probably going to weigh the exact same as you did a minute ago. So we can ignore electrons for that reason. They don't really add very much. If you want to be technical, an electron is about 1/2000th the mass of a proton. So this is 0.0005 of the mass of a proton. So if you were an atom and you weighed 1,837 pounds, 1,836 of those pounds would be your proton, and 1 pound would be the electron. So if we were looking at hydrogen, does that really matter? Hydrogen has 1 proton and 1 electron. So technically we're missing a little bit if we don't count electrons, but we're missing so little it doesn't really matter. Now, every electron has a charge of -1. Remember that protons had a charge of +1. So this is the opposite type of charge. And even though this is an electrical charge, think of it like magnets. We know that magnets have 2 different types of ends. So electrical charges come in 2 variations also: positive electrical charges, negative electrical charges. Now, whenever we look at an atom, the number of electrons is always exactly the same as the number of protons. Well, every proton has a charge of +1. Every electron has a charge of -1. Since there's the same number of protons in an atom as there are electrons, this means that even though we have some small pieces inside the atom that have a positive charge, we have some small pieces that have a negative charge, all the positive and negative charges, what? They cancel each other out. Kind of like if you make the same amount of deposits in your checking account as you have withdrawals, you have the same amount of money as when you get done. You put in $2,368, you withdrew $2,368. You're back wherever you were before you made your deposit or your withdrawal. So this means that when we look at the atom overall, atoms have a charge of 0. Same number of positive charges as negative charges, so all those cancel out. So even though an atom has some positive charges, some negative charges, and remember, we've got those neutrons too that don't have any charge, an atom never has a charge. Now, besides looking at the mass and the electrical charge, the third thing we've been discussing is where things are found. And electrons are not inside the nucleus, they're outside the nucleus. Notice here, this is an atom of helium, and helium has 2 protons, so 2 positive charges, and 2 electrons, 2 negative charges. The most common form of helium also has 2 neutrons. So the 2 positive charges in the protons exactly cancel out the 2 negative charges in the electrons. The neutrons don't affect things one way or the other. So when we think about this, this means that our atom is electrically neutral. But remember when we talked about neutrons, we said atoms don't always have the same number of neutrons. Well, it turns out atoms can't gain or lose protons very easily. That takes a nuclear reaction. But atoms gain and lose electrons all the time. That's very easy to do, partly because of the fact that the electrons are out here kind of on the outer edge of the atom. So it's pretty easy to strip an electron away from an atom or to add an extra electron in there. Now, the problem is if we get an extra electron in our helium so that now we have 3 electrons, notice we don't have the same number of electrons as we do protons anymore. Or if we lose an electron, we don't have the same number of electrons. So if you remember what I said just a minute ago, an atom always has the same number of protons and the same number of electrons. Can't get away from that. So this means when we think about our atoms, if we gain or lose an electron, we don't have an atom anymore. So if we see a situation where we have an atom and we gain electrons, now it has more electrons than protons. And since electrons have a negative charge, we now have more negative charges than we do positive charges. So when we have a particle that has a charge on it, whether it's positive or negative, we don't call it an atom anymore. It's an ion. If we have extra electrons, it's a negative ion. So for instance, one of the elements that we'll talk about is oxygen. And when oxygen forms an ion, it usually forms an ion that has a charge of -2. Notice that the 2 is written first and then the negative sign after that. Notice that this is written above the line of the chemical symbol. So this is O, 2 negative charges. So this is an oxygen ion. If it was just O, it would be an oxygen atom. So this means it has a charge of -2. So this has to have gained 2 electrons. Oxygen has 8 protons. So this means this O-2 ion has 10 electrons because it's got 2 extra electrons compared to the number of protons. So 8 protons, 10 electrons. Cl is chlorine. And when chlorine forms an ion, it forms an ion with a -1 charge. Notice we don't write a 1 here. Just like in math, if you have an equation in math that says x equals 6, we don't write down 1x equals 6, we just say x equals 6. The same thing in chemistry. If the charge is -1, we just say minus, and we understand that there's a 1 there. Now, even though this element is called chlorine, this is actually called chloride. So sometimes if we have negative ions, the name changes slightly. So I'll try to point that out whenever we see one, but we won't be learning how the rules for naming work. Again, that's more a subject for a chemistry class. So if you want to know, I would be happy to meet with you and talk with you, or if you have a chemistry class and you need help, I would be happy to help you, but we're just going to do the basics that we need to do to understand the chemistry that's important in biology. Now, suppose we have an atom that loses electrons. Well, if we lose electrons, now, if you think about it, this means we have fewer electrons than we do protons. If we started out with 11 protons and 11 electrons, and we lose 1 electron, now we have 11 protons and only 10 electrons. Since electrons have a negative charge, if we lose electrons, we're going to have more protons. We're going to have more positive charges. So this is now called a positive ion. So for example, K plus is a potassium ion, and it has a charge of +1, which means it's lost 1 electron. Notice this is another example where we're not writing that 1 in there. We just write plus. We understand that it's a 1. If it's not 1, if it should be +2 or +3, we're going to put the 2 or 3 in there. And this is going to be a common pattern. We're going to be seeing a lot of examples as we discuss chemistry where when there's 1 of something, we don't write 1. We just understand it's 1 if we don't have any number associated with it. So we want to keep that in mind. Now, when we look at the chemicals that we find in your body, and not just in your body, but even chemicals out in the non-living environment around you, what we see is that we don't see very many elements that are just oxygen by itself or just hydrogen by itself. Those are pretty rare. Usually what we see is groups of atoms that are connected to each other. And they're connected through something called chemical bonds. And we'll talk more about chemical bonds later. But one example of a molecule that probably everyone has heard of is H2O, which is water. Now, when we write this formula for a molecule, we write the symbol for each atom. So here's hydrogen. Notice there's a number written behind the hydrogen and it's down below the letter. This is called a subscript. And this tells us how many atoms there are for the element in front of the subscript. So this tells us there are 2 hydrogen atoms in water. The other part of water is O, oxygen. And notice there's no subscript, there's no number written behind the oxygen. So remember what we just said, no number, that means there's 1 atom. Now, when we look at molecules, there are 2 major types of molecules. If we have something called a molecule, it's just some atoms combined to each other with bonds. So there's N2, which is nitrogen gas. And in the air that's around us, even though we think of oxygen as being the important part, nitrogen actually makes up about 78% of the air around us. Oxygen, the oxygen that we need to breathe, has the formula O2. And this is about 21% of the air. So notice between the nitrogen that's in the air and the oxygen that's in the air, this is 99% of the air. So there are a lot of other gases in air, but all the other gases put together only make up about 1% of the air. It's mostly nitrogen, about 4/5, and it's about 1/5 oxygen. So there's just barely anything else. Now, another type of gas that's found in air is something that has the formula O3. And O3 is a molecule called ozone. Whereas O2 only has 2 atoms of oxygen, O3 has 3 atoms of oxygen. Now, ozone is very important for us up in the upper layers of the atmosphere. It helps screen out harmful ultraviolet radiation that reaches the Earth from the sun. And ultraviolet radiation can cause skin cancer when it strikes your skin. It can cause cataracts when it hits your eyes. But most of the ultraviolet radiation from the sun doesn't get to the surface of the Earth. Now, even though ozone is very useful in the upper layers of the atmosphere, at ground level, ozone is actually a harmful pollutant. If you ever watch any of the pollution warnings, sometimes they'll give you warnings for pollen or for mold and things like that that are in the air. But you'll sometimes hear, especially during the summer here in the Chicago area, sometimes there are ozone warning days where they suggest that you shouldn't go outside and exercise because there's more ozone in the air at those particular times. Now, as long as we have at least two atoms together, like N2 or O2 or H2O, the example that we looked at a moment ago, this is a molecule, sorry. But there's one special type of molecule called a compound. If we have a compound, we have to have atoms from at least two different elements. So notice N2 is a molecule, but it's not a compound. O2 is a molecule, but it's not a compound. O3 is a molecule, but it's not a compound. Why? Because in N2, all the atoms, well, both of the atoms are nitrogen atoms. In O3, all three of them are oxygen. So to be a compound, you have to be a molecule and you have to have at least two different types of atoms. So H2O is a molecule, but H2O is also a compound. The other formula that most people have heard of, NaCl, what we sometimes call table salt, that's a molecule, but it's also a compound. Now, we do find some H2O in people. We don't find very much NaCl, even though you might eat salt in your diet. Once it gets in your body, the sodium separates from the chloride. But most of the molecules in not just your body, but any type of living body are much larger. So for instance, you've probably heard of glucose. This is the blood sugar that we hear about that diabetics have to monitor and regulate. We all do, it's just that some of us, our bodies do it for us. But glucose has the formula C6H12O6. So notice this means that there are 6 atoms of carbon, because the subscript behind the 6 is C. There are 12 atoms of hydrogen, the subscript behind the H is 12. And there are 6 atoms of oxygen, the subscript behind the O is 6. Another molecule you've probably heard of, cholesterol. Cholesterol has the formula C26H47O. So in cholesterol, there are 26 atoms of carbon, 46 atoms of hydrogen, and notice no number with the oxygen. So what? Just 1 atom of oxygen. So glucose and cholesterol are molecules, because a molecule just means we have more than 1 atom stuck together, but they're also compounds because all the atoms aren't the same. Now, after our test on Monday, we're going to work some problems involved with some of these things. But for now, I'm going to let you go. And I would suggest for now, don't worry about chemistry until after we finish with the test on Monday. Unless you have enough time over the weekend, you can do both. In which case, then do both. Are there any questions about chemistry before we leave this paper? Okay, I will let you go now. Keep in mind, I posted another assignment yesterday. This one is a short quiz on identifying the steps of hypothesis testing. So it gives you a real life example and asks you to match the step with the description of what's occurring. You don't have to turn that in till Monday, but if you turn it in by Sunday at noon, I will grade it and send it back to you so that you can look at it if you want to use it to study for the test. But otherwise, I will let you go. So enjoy the long weekend. I guess they're all long weekends in summer. And I will see you Monday morning. So don't forget, I'll send out an email, but remember the test will start I don't think it will take you the full time, but you will have till 9:55 to have your test timestamped. So enjoy the weekend. If you have any questions, go ahead and ask them before we leave. Otherwise, I will let you go. And keep in mind when you're logged in, I can see your chat messages. It's just that I don't usually know them because I'm so focused on what we're lecturing on. So if you have something directly related to what we're talking about, it's usually just to break in and ask the question out loud. I know some teachers don't like to be interrupted, but that will never bother me if you interrupt me.